All right, let's jump right in. Today we're going to talk about building a bridge between the abstract numbers you see in a classroom and the very real world around us. We are diving into the art of mathematical modeling, a skill that, honestly, is like a superpower for turning equations into actual real-world solutions.
You know, we've all been there, staring at a whiteboard full of X's and Y's in math class, thinking this exact thing. It's the age-old question every student asks, trying to figure out why any of this matters. And it turns out there is a fantastic answer.
And that answer is mathematical modeling. It's this really powerful process of taking a messy, real-world situation, translating it into the clean language of math, and then using that to figure out a solution. But here's the catch. It sounds straightforward, right? But for a lot of students, this process is like a maze where they just get stuck and hit a dead end.
So let's start right there with a fundamental challenge, actually putting math to work. Because applying these abstract concepts isn't just about knowing the formulas. It's a whole separate skill, and frankly, it's a lot harder than it looks.
Okay, so take a look at this. This is the full, formal process for mathematical modeling. It's a 7-step cycle from researchers Blum and Lice. And just, wow, look at all the mental steps you have to take. From constructing a mental model and simplifying it, to doing the math, and then, and this is key, interpreting and validating your results back in the real world. It's really no wonder students get lost somewhere in this cycle.
So, if the process is that complicated, how in the world are we supposed to teach it? Well, that brings us to this really cool idea of building a temporary support structure, a scaffold for the brain.
The theory behind this is something called the zone of proximal development, or ZPD for short. Just think of it as the absolute sweet spot for learning. It's that space where a task is just a little too tough for you to do on your own, but you can do it if you have the right guidance from a teacher or even a friend. It's where real growth happens.
And the tool that helps you cross that zone? That's called scaffolding. And it's exactly what it sounds like. Just like the scaffolding on a building, it is a temporary support structure. It gives you just enough help to tackle the problem and build the skill yourself. And then, once you've got it, the scaffold comes down. They're basically training wheels for learning complex ideas.
So with that in mind, researchers created a scaffold specifically for mathematical modeling. They took that really intimidating 7-step cycle we saw earlier and boiled it down to this much more manageable 4-step process. It's designed from the ground up to support students who are totally new to this.
Okay, so that's the theory. But how did it actually work in practice? Well, researchers set up an experiment to see if this whole scaffolded approach could really help student teachers build up their modeling skills in a real classroom setting.
Here's the setup. They got 55 student teachers and split them into 10 teams. And to keep things realistic, each team was a mix of students with high, moderate, and low math achievement. The mission was to solve 2 different structured problems, using that simplified 4-step modeling cycle as their guide.
The first task was a classic business puzzle. So imagine a sweet factory has limits on how many chocolate-covered nuts and raisins it can make. The students had to figure out the perfect product mix to make the most money. I mean, it's a super practical, real-world kind of problem.
The second task was a nutrition challenge. The groups were given a table with info on 3 different diet foods. Their job? Calculate the precise number of ounces of each food a person would need to eat to hit their exact daily nutrient targets. Again, you can totally imagine a nutritionist having to solve this for a client.
All right, so after all that, the big question. Did the scaffold actually work? Let's get into the results.
And the initial results were fantastic. Get this, all 10 groups, every single one of them, successfully got the process started. They could read the problem, pull out the important info, and make the right assumptions to turn it into math. That first big hurdle, everyone cleared it. But it wasn't a complete home run. When it came to actually doing the math, things were a bit more mixed. About 70% of the groups got their math procedures right, but 30%, they made some mistakes. So the scaffold helped them get in the door, but the math itself was still a real challenge for some.
And this, right here, led to the most fascinating result of the whole study. One of the groups, working on that nutritionist problem, did their math and came up with an answer that included a negative number of ounces for one of the diet foods. As the researchers dryly noted, this is, of course, an unrealistic solution. You can't eat negative ounces of food.
Which brings us to the key question, right? Why would a group of students look at a physically impossible answer and just accept it? Well, the researchers noticed that the group never stopped to ask themselves if the answer made any sense in the real world. They just did the math, got an answer, and wrote it down. They completely skipped that crucial final step of checking their work against reality.
And that failure is actually the most important lesson of all. It takes us to our final section, because this isn't really just about math anymore. It's about learning how to learn and how to connect what you know back to the real world.
So what are the big takeaways here? Well, first, it's clear that strategic support, scaffolding, really does help beginners get started. Second, simplifying the task is a great way to ease into a complex new skill. Third, the process helps build not just the skill of modeling, but also the math skills underneath it. But the biggest one is this. Even with all the help in the world, that final step of interpreting what your answer means in reality is absolutely critical and maybe the hardest part to teach.
And that's why this is so important way beyond this one study. What we're looking at is basically a blueprint for how to teach any complex skill. It doesn't matter if it's learning to code, writing an essay, or playing the guitar, the principles are exactly the same. Break it down, provide some temporary support, and always connect it back to the real world.
And that leaves us with a final question to chew on. We've seen how powerful this approach can be for something as abstract and tricky as math. So just imagine, what other complex skills that seem totally out of reach right now could we finally master if we just had the right scaffold to help us get started?